In this video, we're going to start to think about what do the atomic orbitals actually look like? So we talked about how to assign them with quantum numbers, and we've talked about how to use in other cases. But what do they look like in 3D space? Because we need to know what they look like so that as we move forward in this video series, we can actually think about, how do bonds form? How do we make a molecule? So let's think about the s orbitals. So if we look at the wave function, in many different time periods, we will get this information. If we plot the probability density in terms of R, we get this. Whoops, it does not go below 0. Let me try that again. So what we see is that the probability density is quite high close to the nucleus, and it moves forward. If we look at the total radial probability, so we are going to use a different mathematical function to calculate the most likely radius. So this tells us not that the electron could be super close to the nucleus. It tells us that it's most likely at 52.9 picometers for the 1s orbital. So this is what the 1s orbital kind of looks like. If we were to draw it ourselves, you would get a sphere. With x, y, and z, you can really put the orbitals in any direction. So what we see is a sphere, but it's going to look more like a layered onion. So we have this 1s orbital where the electron is most likely on the line of the sphere. So what happens if we look at the 2s and 3s? So if we look at these graphics, and I'll zoom in a little, we see something very similar where we get a summary photo, but the overall structure of both of these is still just a sphere. But if we look inside, we can see a layered onion. If we look at the probability density and the total radial probability, what we see are places where it's equal to 0. And this is what's called a node. And so the other thing that we can kind of notice is that the 1s orbital, there's a chance it could be in the 1s for the 2s, and a chance it could be in the 2s. And for the 3s, we see 1s, 2s, and 3s. So this would be the 1s, 2s, 3s. So there's a chance, but we really see that it's either in one of those orbitals or not. But what is this node? So a node is a place where the probability of finding the electron is 0. If we think about a wave, this is a place where you would expect this to be a node. So if this were to rotate in 3D space, these would be stable. So the nodes are present in all orbitals, but the number of nodes is equal to n minus 1. So in n equals 1, there are no nodes, but in n equals 7, there are going to be 6 nodes. So the movement of these nodes tells us that there are points where psi and psi squared pass through 0. So what are the shapes of the other orbitals, such as the p orbital, d, and f orbital? For the p orbitals, we know that L equals 1 and m sub L equals -1, 0, and 1. This tells us that there are 3 equivalent orbitals. Those orbitals are called the px, py, and pz orbital, which basically means that we see this dumbbell shape on either the x, y, or z axis. So if we were to draw this, and this is the x-axis, the orbital would look something like this. The y is along the y-axis, the z is on the z-axis. The radial probability, or the total radial probability, essentially shows that more than likely the electron is at the apex or the peak of this orbital. But there is a node between the two orbitals, so you can see that in all of these images. So this tells us that these m sub L values correspond to px, py, and pz. So if you know that an electron is in the px, it would have one of these 3 values. In these video series, we're not going to assign those values, but they are assigned. So let's look at the d orbitals. There are 5 different d orbitals, which means that m sub l is equal to -2, -1, 0, 1, and 2. And they are along different axes. So when we look at these, we can see that there is this cloverleaf shape that corresponds to the dyz, dxy, dxz, and the dx squared, y squared. And there is a single other shape of the dz squared. These 5 orbitals correspond to the 5 m sub l values. We don't typically draw these a lot in these video series, but it's something we want to keep in mind that there are 5 of them and they are each unique. So let's look at the f orbitals. So there are 7 f orbitals. So the m sub l values are -3, -2, -1, 0, 1, 2, 3. So an f orbital has a L value of 3. And you can see that these have perhaps even more diverse shapes. But the shapes of these basically tell us that there are different places where the electrons could be. And these different places are found throughout the different structures. So atomic orbitals, if you were to shove all of these orbitals, so you can see the yellow d orbitals, the red p orbitals, you can't really see the other structures, but they're all in here. So the combined shape is a sphere, which is why typically we draw atoms as a sphere. And it's going to be important for us to think about the phase of these orbitals. So for an s orbital, it's going to just have one phase. And the phase is basically saying that it could be positive and it could be negative. So this would be the positive, this would be the negative. For a p orbital, you have a plus and a minus. Whoops, that's not the way that minus signs go. Let's fix that. So the phase of these orbitals is going to be really important for how they interact to create a bond, which we'll see in later videos. So when we think about the atomic orbitals, the shapes of those gives rise to the overall atomic shape. And these orbitals are going to be essential for finding and creating bonds as we move forward.